Okay, welcome back to the special topics of semiconductor technology. Today we are looking at the last section of chapter 3. We're going to discuss the so-called basic circuit concept. Okay, let's talk about what kind of circuit are used in semiconductor industry. Basically, all those circuits, including bipolar junction transistor, bipolar transistor IC, PMOS, NMOS, and CMOS, the complementary MOS, also called inverter. Okay, and later we'll discuss what kind of inverter, how it works, and by taking advantage of the bipolar junction transistor and the MOS, we have the so-called bipolar junction transistor CMOS, BiCMOS. Okay. Let's look at the device that with different substrate. According to your applications, okay, then you need to choose the right substrate to build your IC. And basically, for silicon, it's just a simple materials which being used as the substrate to creating a special function came from the logic design of those transistors. It serves only as a substrate. Doesn't need to have particular performance of the intrinsic property of itself. You're using the semiconductor property concept to build bipolar junction transistor, build MOS, BiCMOS. All these basically dominate the IC industry. It should be more than 90% of those IC using silicon as a substrate. You can also using germanium. Germanium is the same as silicon, the element in group 4. When you build the IC using germanium, it can have a faster mobility than silicon. We're talking about electron and hole mobility in silicon and in germanium, the comparison between these two substrates. So electron can move faster in germanium than in silicon. So if you use germanium as a substrate, you can have high-speed device and using bipolar junction transistor. It's fast, but you can creating a lot of heat. So in general, bipolar junction transistor, you're going to have a large heat sink. You have a large plate of heat sink on the back of the IC to dissipate the heat generated for the power device. If you are using compound semiconductor, for example, silicon carbide, or gallium nitride, okay, or gallium nitride, gallium arsenide, etc. In general, the compound semiconductor has a very special band structure, electronic configuration band structure, very special. So you can use all those spatial band structure to creating specific physical phenomenon. For example, for gallium nitride arsenide, it can be used as a high-speed communication chip. Okay, the electron move approximately 4 to 5 times faster in gallium nitride compared to in silicon. So you can have higher speed communication application for gallium nitride. Its atomic configuration, the electron configuration, has a very special phenomenon that can creating a light emitting diode with red light. It can emit red electromagnetic radiations, red LED. Okay, so when you're using compound semiconductor, you're actually looking at the very special property of the material itself. Let's see. For basically for the MOS, using the substrate as silicon, it should be go up to about 90%. Okay, because a lot of applications simply using the substrate to build whatever IC you need, whatever function you need on top of the silicon wafer. Bipolar junction transistor using for power chip, higher communication required, and also because of high heat consumption, so sometimes maybe will cause some problem if your IC getting smaller and smaller. Okay, heat dissipation is a big problem for the bipolar junction transistor. And for compound semiconductor, it only composed of less than 5% here. As I mentioned, compound semiconductor, you are actually looking at its a very specific function. Okay, very specific function of its electron configurations. For the bipolar IC, this is the IC being built the first. In 1961, at Fairchild Camera, they're actually using 4 bipolar transistor to build a first IC. Okay, build first IC, and at that time it cost $150 per piece. It's very expensive at that time, but its market share is reducing rapidly because of heat dissipation problems, and also you have some other IC can be used to substitute for bipolar IC, but it's still used for the analog system and the power device to creating large current to drive a lot of the components. Right now it's still using, say TV, VCR, cell phone, etc. Okay. For the PMOS, okay, it is the first MOS built for the MOS structure in 1960. MOS, and the difference between MOS and bipolar BJT is bipolar junction transistor is basically used for analog system. using the amplifier property, amplification of the power. Okay, use it at the analog system. But for MOS system, it doesn't have the power amplification properties, only serve as a switch, so you can only have 1 and 0 signal coming in and out. So this is only good for use as for digital logic device. Okay, and later on replaced by NMOS, because NMOS is basically operated by electron, and electron has higher mobility than Hall. Okay, so it can run at a faster speed, response time which quicker than PMOS. So for the NMOS, it's faster than PMOS because the mobility of electrons is faster than Hall. And also it can be used as a digital logic device. Okay, and later on it's being replaced by CMOS, complementary MOS, after the 1980s. The CMOS has better stability than NMOS. Okay, also has better resistance to the noise. So even though the process twice as much as a single NMOS or PMOS, but because of the quality and the low power consumption and better signal, okay, immunity, so noise immunity. Okay, so it's a much better design than simply NMOS or PMOS. So basically right now all the MOS you build in the fab is a CMOS. Okay, the CMOS is the most commonly used circuit IC chip since the 1980s. The reason is of its low power consumption, high temperature stability, noise immunity, and a symmetrical design. Okay, symmetrical design because it's complementary. That means for that MOS, you've got PMOS, and also you have NMOS. Okay, and here you have insulator. Okay, basically you build a CMOS to the left and to the right. It's a symmetrical design. Okay, that kind of design will give you a better quality and low power consumption. Okay, this is the electronic symbol for CMOS, and let's look at what is CMOS and how does it being called by inverter. This is a CMOS structure at the center over here. You have voltage in, signal comes in, signal comes out. Okay, let's look at it. If you have signal comes in as 1, high voltage. Okay, let's say this is high voltage. And for high voltage over here, you were creating a electron over here, but this is PMOS. You are supposed to have P channel, but because you apply a high voltage, so you actually creating more electron at the silicon wafer side. So you are not going to creating a PMOS. So this is not going to be connect. Okay, current not going through. So the V out over here, we are not able to read the signal from here. But for the high voltage here, you're actually creating an electron. So you can help to creating an N channel here. So this is going to be electron going through. So what a VR read? VR read is the ground level. So when you have high voltage 1 goes in, the VR will be the ground 0. Okay, we say this is inverter. Input 1, output 0. Input 1, output 0. Let's look at it the other way. If you have low voltage, input 0, okay, the voltage less than 0, okay, I mean your VG less than 0. So at NMOS part, the negative charge will attract particles, hole over here. But you are supposed to creating an N channel, and you end up with more and more hole at the silicon wafer side. So this NMOS will not have current going through. But low voltage here on top of the PMOS will resulting more hole occur over here. So that is why how PMOS operate. So that means this will have current going through. So that means your V out will read the voltage level of VDD. Okay, so that means when you input 0, you have output 1. This is called inverter. Right? So this is This is the so-called complementary MOS, combining a PMOS and an NMOS. When you input 0, output 1, output 0, input 1. This is the inverter CMOS. So your output still 0 and 1, always binary system, 0 and 1 binary system, although it has an inverted signal coming out. This is called CMOS, also called inverter. This is how the so-called symmetrical design of the CMOS. This is N channel, NMOS here. And this is PMOS here. Well, this is very simple schematic design, the view of the CMOS. Okay, it's not just that easy. Okay, but just show you it's a symmetrical design of MMP MOS area for the CMOS structure. They actually has a gate area to connect with each other. Okay. The so-called BiCMOS is a combination of CMOS and bipolar junction transistor, taking advantage of both. It's mainly developed in 1990s, somewhere 1990s. In this kind of the device, you're using CMOS as a logic circuit, but bipolar circuit for input and output, because bipolar has a faster transition speed. Okay, So this kind of design has a speed faster than CMOS, but with a higher power consumption. Okay, this high power consumption can be a problem in the future. Okay, next let's try to take a brief introduction about the so-called IC. Okay, integrated circuit. IC. Basically, these three kind of IC, three kind of chip, as you say, three kind of chip. First, memory. You know the memory. You play around your computer. You build up your computer, assemble your computer by yourself. So go ahead to buy the memories. Microprocessor, the CPU of your computer. Okay, and application specific IC, ASIC, say your graphic chip, communication, maybe logic. Okay, mathematics. Okay, floating point microprocessor. Okay, you have some of these application. So basically, for the IC chip industry, basically divided by these three categories. You know the memories. Okay, it's a storage device. Okay, to store your data. Okay, and there's a volatile memory and non-volatile memory, DRAM, SRAM, or EEPROM or flash. Okay, if you play around the microprocessor and you know what is EEPROM and flash memories. Okay, and you use a lot of DRAM. Okay, on your computers. What is the DRAM? DRAM is a major component for computer and other electronic instrument for data storage. Okay, it's the main driving force of IC process development. What is DRAM? One transistor as switch, one capacitor as storage. Okay, using this switch to input signal, store the signal, or release the signal. Okay, so DRAM basically is a transistor plus a capacitor. This is a bit, 1 bit of memory. 1 bit of memory. Okay, a transistor with 1 capacitor. This is so-called memory. So how much memory you have in your computer? You may have 8 gigabyte or 16 gigabit. Okay, every single bit is this. This is 1 bit. 8 giga. 8 times 10 to the 9 unit of this 8 gigabit. So you can think about how many devices, how many switch and capacitor put into your computer, put into your memory chips. Okay, so that's how we need to push the manufacturing process to go down as small as possible, so you can have more device input into a chip. That will give you more powerful application. So again, let's say right now in the fab for TSMC, basically for the fab, what they build is basically CMOS instead of PMOS or NMOS alone, because for the CMOS it has low power consumption, high temperature stability, and high noise humidity. So that means you get good quality of chip. Okay. Alright, this is the inverter we had just discussed. Okay, the in and out. Input 0, output 1, input 1, output 0. So you always has signal as 1 and 0 binary system for electronic device, binary systems. Okay, here we showed you that two cross-section graph of a CMOS using an early stage technology and most sophisticated technology we are using right now. Okay, this is CMOS using maybe in 1960, 1970. The structure here is called locus. A very typical process creating an image like this. That's called locus process. We will discuss that in the future. So you basically have a CMOS here. So let's look at here. You have PMOS. Okay, no, NMOS. You're going to creating an N channel over here, and this is PMOS. You're trying to creating a P channel over here. So NMOS, PMOS, that's cut in half. Basically have the similar configuration. Okay, so that's what we say symmetrical design. And in this graph you have two metal layer. Okay, two metal layer. First here, the first layer, second layer, and we use aluminum, copper, and silicon, an alloy for the metal wire, for the conducting wire. And in the future we're going to try to tell you why not aluminum only, but aluminum with very little amount of copper and silicon combining together to form the metal wire. Okay. In practice, normally when you try to describe an IC, whether or not it's easy to build, to fabricate, there's two ways to describe an IC, the complexity of fabrication. The first is how many layers of wire required for the IC. So over here is 2 layers. Okay. The other way to describe the process is how many masks, number of masks required to creating this structure. Okay, two ways. One is how many layers of wire. The other is how many masks required to creating the structure like this. Okay, for this diagram, use aluminum as the primary conducting wire. Next, this is using copper. These are copper. These are copper. Again, 4 layer of metal wire using copper as the conducting wire. And you see the difference here. Okay, from the outlook of the geometry, the cross-section area, you see a lot of difference. Okay, so that means aluminum technology is quite different to copper technology with respect to the conductive wire manufacturing process. For copper, basically it's called a damascene process, dual damascene process, to creating a conducting wire like this. They were using the traditional electroplating technique to produce the structure like this in one step, electroplating. Okay, it's quite different process compared to the aluminum. So for the fab, normally it's a fab using aluminum. It will not mix up with the copper technology. Okay, so this building is for aluminum, is all for aluminum, and next building may be copper technology. Okay, because copper being looked as a contamination for aluminum technology, because as we mentioned, you can using a process or etch process to remove materials. Copper basically cannot be etched. Okay, well, it's not really cannot, but it's very difficult for the process design. It's very difficult to be etched away. You may end up taking several processes to etch away copper. But for aluminum, it's a simply one-step process. Gas goes into the furnace and react with aluminum and form gaseous product and being exhausted. So you can etch away the aluminum quite easily, but not copper. So that's why copper using the so-called damascene process, using electroplating method to fill up the it looks like 2 layers of copper together, and you have excess copper. You have excess copper after electroplating, and then polishing, grinding and polishing away. So you can see a lot of horizontal line. You see the horizontal line here. That means grinding and polishing. Grinding and polishing process. Okay. Because the excess copper cannot be etched away. It has to be grinding and polishing away. And again, you can see this as a quite similar symmetrical the structure for the most. Basically the same structure. So that's we say it's a symmetrical symmetrical structure. So you can using maybe a set of masks to creating 2 different modes at the same process design. Okay, that'll be all for this section. Let's look at the summary for the chapter 3. Chapter 3, we discussed what is semiconductor. Okay. It's the material with conductivity between conductor and insulator. And for single crystal semiconductor, its conductivity can be controlled by dopant concentration and applied voltage. Okay. The higher the dopant concentration, the better the conductivity. You can using silicon and germanium as a pure element substrate, or using gallium arsenide for compound materials. Basically, silicon is the most popular one. It's abundant, it's stable, easy to form oxide, and oxide is very good quality. Silicon dioxide. And for p-type dopant, it's in group 3. Okay, in group 3A, boron. Boron is used for the p-type dopant. Okay, and its majority charge carrier is Hall. Majority charge carrier is Hall. And for n-type, okay, there's typo here. For n-type semiconductor, the dopant will be phosphorus, arsenic, or bismuth. And the majority charge carrier will be electron. Electron possess negative charge, so we call n-type. Okay. As we mentioned, the higher the dopant concentration, the better the conductivity, so the lower resistivities. At the same dopant concentration, n-type semiconductor has a lower resistivity than p-type because of electron has better mobility. Electron has better mobility than holes, so it moves faster than Hall. And we also discussed about the basic devices. Okay, the basic devices: capacitor, resistance, and the capacitor can be used in DRAM combined with a MOS, okay, to being served as a storage device. And for bipolar junction transistor can be used to amplify electric signal, and we call current gain beta equal to current coming through collector divided by current coming through to the base, and this is called current gain. How many times of amplification of the current. And this kind of application using the power gain and the current gain, you can use this for an analog system. But for MOS, basically used for digital system, digital logic, and both transistors can be looked at as a switch. Okay, both bipolar junction transistor or MOS, it's basically a switch that can give you on and off signal. That's 1 and 0 for binary system, for the electronic systems. Right now, the MOS is the dominant IC. Okay, for the IC industrial. you can divide it by the categorize the IC into three kind of product: memory, microprocessor, and application specific IC, ASIC. Okay. The advantage of CMOS used in the fab, the fabrication in the fab, instead of simple PMOS or NMOS, that's because of low power consumption, high temperature stability, and high noise immunity. Okay, and that, as we mentioned, this means good quality for CMOS. Okay, so right now in the fab is the location environment. We build the IC, we build the transistors, build the diode, build the capacitor. We call fab. Okay, and right now the primary product for the fab application is transistor, that is MOS, especially CMOS. Okay, that'll be all for chapter 3.